Okay, welcome back everyone. So in the last video, we talked about the concept of the ANOVA and what it's for. In this video, we're going to be talking about an overview of computing the ANOVA and what that means, both in terms of the analysis and in terms of how design impacts what your analysis can show. So we're going to begin with looking at computational formulas. And again, the difference between computation and definitional, you guys can use when you're comfortable with. I like using the computation just because it makes it easy to visualize some things in terms of what's happening with this analysis. So at the core, if you remember from the last video, there's three main things we need to figure out. That is the total variability that's in our data set that's produced. And then what is your manipulation contributing to that variability? That's what it can account for. And what is just left over? What's just kind of the random stuff that happens that's out of our purview, or maybe things that we didn't control for. So that gives us the sum of squares total, the sum of squares between, and the sum of squares within. So what we're going to be talking about is how to calculate those, and then how do you actually think about those in terms of interpretation. So if you remember how this works out, that these two things, between and within, have to break out of this. So the first rule was that neither one of these can be greater than the total. And one of the first things that usually happens when people used to have to do this by hand is that they always forget this term, particularly if they're using computational formulas. They forget to subtract this out. And so when there's an error, that's typically it. And this happens a lot when you start doing more expansive designs like factorial designs, because there's a lot to keep track of. But in either case, you always have to remove this part. And the way I'm going to try to couch this is that what this serves is, if you remember our just general rule about measurement, that every measurement is comprised of the true score and some level of error or some level of movement around that. And so in a way, this reflects that kind of thinking, that the sum of squares total is our general or measure that we're taking, and it's comprised of the measure that we want and some variation. Now, the way this is going to work is a little bit backwards, because what happens is that this term is going to end up being kind of our mean value, our center value, and this is the deviations from that. So again, remember that sum of squared deviations from some score. That's what this refers to. So we're going to take every score, individual score, and we're going to compare that to some grand mean measure, and means in quotes because it's not quite a mean in the sense that we're used to talking about it. And when we get here, we're going to be talking about the same thing. Now we're going to be looking at groups across some change here, and then we're going to be looking at individual scores within a group and looking at the influence there. So that's the breakup here. So one thing to note is that this term is the same in both places. So the term that we generate here as our variability, our deviation effect here, becomes our mean effect here. So I'm going to just use this kind of language where all these are kind of your deviations away from some mean value from that. And we're looking at what's accounting for spread. So what's accounting for this distance? The total will give you the biggest difference, or the total difference that exists in your distribution. And then the bottom two now tell you how to distribute that or account for that. So conceptually, that's what that looks like. Let's put some numbers to this. So here I'm just going to make up some numbers. And again, we're using the example that we've been talking about in class for a while, this idea of arranging seating so that we can encourage conversation in these areas. And so we had a couple manipulations, one where we took out the middle table just to move the spacing in, and then two where we arranged it so they're facing each other. With the hopes that this is going to increase either the number of conversations or the length of conversations. You can choose whatever you want those numbers to represent here. But I'm going to give you some mean data. So say we had 7 people in each condition, so a total of 21 people, and they've mapped out like this. And so what we need to get in order to start these computations to get these values is a few basic things. So we're going to need to get a sum. So all this number is just the sum of these numbers. Then we're going to get the square sum, which is basically square 10, square 12, square 7, square 5, so on, and add them, and that's going to give you this number. And then this third total is this sum squared. So that's going to give us kind of our variances to work with. The next two terms down here are just our mean and standard deviation. And this is just descriptive. It just gives us an idea about what this particular distribution looks like in this group. And what you can see is that, again, looking at eyeballing your data is fine. It looks like there's something happening because we're seeing this doubling here from 6 to 12. And that 12 is pretty consistent across these two conditions. But we're also seeing an increase in variability. So this may cause some issues later down the line, but we'll see how that plays out. So the first thing we need to get is our sum of squares total. And to get that, we'll need these grand totals. So this 217 is basically these three values added. This 3357 is these three added, combined. And then this 47,000 number is 217 squared. So that gives you your grand totals. And again, your large N is 21. So that's going to give us what we're going to need for our sum squares total. Then what we're going to do is break this data up. So the first thing we're going to do is break it up by group. And this is going to give us our sum of squares between, which is looking at the variability that's produced by being in different conditions. And then finally, we're going to regroup these and look at them as an aggregate, and now seeing how much variability is attributed to just by individual differences in scores or people, if you will. So remember, in the between design, each one of these groups is getting a separate group of people. So this is 7 people here, 7 more people here, 7 more people here. All right, so let's look at what this looks like number-wise. All right, so first thing you see is that we're taking that squared value, which we summed before, and then our sum score squared, and then dividing that by our sample size. And that's going to give us this number here. And so what this will give us is when we do this out, so do this calculation, that becomes this, and the remainder is 1114. So that's the amount of variability that's in our data. That's the size of our distribution, if you will, for this particular experiment. That's the total variability. We haven't differentiated yet. This is just everything that's there. Now we're going to start breaking this up and trying to see what can we account for. So the first thing we'll do is our between. And what we're using here are the sum of squares, those middle totals that we had here. So let's go back here. We're adding these three totals to get these numbers. Dividing by 7, that's small n, and that is the number of people in each group. And then we're subtracting this correction term, the same term here. And what we're getting is 160.39. Now, hold on to that thought for a minute. I'm going to come back to that because this is important. Now we're going to look at the within value. And same thing, now we're going to use this same number as the same as here. So we're looking at all the scores. But now we're subtracting that from the group deviation rather than the total deviation here. And so that's giving us 954. Now what I want you to eyeball here is the relative size of these three values. So we talked about this conceptually, what we meant when we looked at the extremes, when the between value is getting close to your total value or the within value is getting close to your value. And what we have here is that the within value is pretty close to our total. So that probably is going to mean that most of the stuff we're seeing here is due to random stuff that we haven't accounted for. Doesn't appear to be a lot going on here. Now, that's just an eyeball. When we actually calculate, we're going to do something different because remember, we're not dividing these terms, we're dividing variances. And variances are basically this value divided by the degrees of freedom. The degrees of freedom in this case is 2 because there's 3 groups, minus 1, that's k minus 1. And in this case, it's n minus k. So total big N, 21 minus k, which is 3. So that gives us 18. So when you divide this out, this is what you get. So the amount of variance we're accounting for is 80. The amount of variance we're not accounting for is 53. So the F ratio of 2 and 18, again, these are degrees of freedom for effect and random, or within error, is 80.2 over 53, which gives us 151. Now, I'm not going to look this up. I'm going to tell you that this is not going to be significant. We've attributed for a little bit more variability with our effect than we do with chance, but it's not enough to be significant. So at this point, we actually can't say that changing the arrangement of the seating has made a difference in the amount of conversations for here. But what this tells me is that there is something here. Let me get my cursor over here. This number here tells me that there was something going on, that there's something we're not accounting for. Now, if you remember our conversation about these designs in principle, remember that between designs tend to have a lot of error because we're using different people in each group. So what if we had a way to account for that? What if we had a way to account for individual differences? And the way we can do that, and the way we talk about this, is by running this not as a between, but as a within design. So we're going to take the same effect, the same data, and act like we use the same people in each group. So that's going to give us the within, or repeated measures, ANOVA. And we're going to use some of the same values. So sum of squares total and sum of squares between are still the same. But now we're going to add this thing here, the sum of squares subjects. And what happens is now we're going to treat each person as their own group. So this T refers to people, So T is a person. And what we're going to do is we're going to get the same kind of deviation value. And we're going to divide this by K, which is number of groups, because that's the actual number of observations we'll get from each person. We're getting this mean value. And again, we're going to subtract that from this same correction term. That's going to give us the variability that's attributed to people being people. And because we're using the same person across conditions, we can account for that. That now becomes something we can account for. So then our error term changes, and this is this SB term. So this is subjects by between. And this is what's left over once we account for individual variability as due to people being people and the effect of our manipulation. And this is what's left over. So this becomes your error term. This is what you're now going to be dividing by. So again, let's take those same numbers. And the point again is what we're doing is we're treating each person as its own group. And what that does is it takes this random variability that would have gone in the error pile and now turns it into systematic. So now essentially you're creating another group. Now let's look at the numbers that we need here. So we're going to use the same one. This is the same total variability. The same effect. We haven't changed the between groups at all. The same effect there. So we're going to hold that over from last time. Now we're going to calculate the sum of squared subjects. And this is the number of those squared values for each participant divided by 3, because again, that's the number of scores. They're all contributing, minus this correction term. And that's going to give us 672. Now, look how much this accounts for. And I'm going to come back to this. So just look at that number there. And then let's look at what's left over. So now that we know our participant variance and we know our effect variance, we can talk about what's left over, and it's 281. This is much smaller. Remember, the original within was 954, but of that 954, 672 of it was due to people being people. Now that we can account for that, that comes out of the analysis, goes in your pocket, and what you're dividing by is this much smaller number. So again, we're going to get the variance, make the mean squared variance here. Your degrees of freedom here is small n times 1 and k minus 1. So it's 6 times 2, which gives you 12. So that's going to give you 23. Remember, the original error term was 50. So for the same effect, we're dividing by a much smaller error term, which has now increased our F 3.42. Now, truth in advertising, this is still not significant. There's still something going on here, but we are in much better shape to see differences there. You're much more likely that that could have been significant than not. And the important thing is, and again, this is where design comes in handy, is that this is not a change in our effect. This is not a change in our manipulation. This is a change in how we brought in participants. This is a change in how we control things. So by doing this within design, by using the same people, you can account for that variability. That takes that part out, and it makes it much easier to see an effect if it's there. Now, the fact that it's not significant tells that there might still be something else that's happening that we're not accounting for. So that might mean we have to do something, or it could be that our effect isn't as strong as it can be. So we might need to include something else to go through. That's what kind of your role as a scientist is going to be. But the thing I want to leave you with is that, again, design matters, not just in terms of your implementation, but in terms of what your analysis can help you say, and in turn, what you can tell your audience. So hopefully this helped. I will see you guys in the next round. Take care, everyone.